Hello, Caymans. Mr. Eicher here, coming at you with part 2 of a lesson about modeling with polynomials. This is kind of an engineering or manufacturing type of question. This question is known in mathematics as an optimization problem. We've talked about optimization with linear programming, optimizing an objective function based on a system of constraints. But in this video, we'll be reviewing formulas for surface area of a cylinder and volume of a cylinder, and then writing a polynomial function and then graphing that to answer a question, kind of a design question. So let's get started. A cylindrical can, a can that's a cylinder, is to be made to hold 500 cubic centimeters of oil. Find the dimensions that will minimize the cost of the metal to manufacture the can. So in manufacturing and design questions, you don't want to just make any kind of shape. You would like to make the biggest possible shape to fit the volume that you need, but you want to use the least amount of materials, because if you're making a lot of these cans, if you're having a lot of leftover material or poorly designed kind of cans, you're going to be cutting into your profits and wasting money. So we need to review first the volume formula for a cylinder and the surface area of a cylinder. So let's actually draw a sketch of a three-dimensional cylinder. So a cylinder you would have maybe looks like this. There's the top of the can, and there's the sides, and then here's the bottom of the can. I like that three-dimensional can. It says to label R, the radius, and H. So R would be this distance. So this would be the radius. And then the height of the can goes from here to here. So this is the height of the can. H equals the height. And we're saying R is the radius. The net of the cylinder, if we tried to cut this can and then uncurl the side there, we would get a circular top of the can. We have a bottom of the can, and then we have the rectangular part that wraps around the can. So we get something like this. This is the top of the can, this is the bottom of the can, and then this rectangle is the part that wraps around the can. It should be a rectangle. It doesn't look like I did a very good job making a rectangle. But we would have the radius of the circle is this distance. The radius of the circle is this distance. And this rectangle has a height here. That was the height that corresponds to this height right there. And then this distance, this length of the rectangle, is the part that would wrap around the circle. And that part is called the circumference, the part that wraps around. So circumference C, the formula for circumference is 2 pi r. So that would be our net for the cylinder. So coming back to the top, the formula for the surface area of a cylinder is you have a circular top, you have a circular bottom, the area of a circle is pi r squared, and then you have an area of a rectangle, which is 2 pi r, the length of the rectangle, times the height, or the width of the rectangle. So the formula would be 2 pi r squared plus 2 pi rh, and that would be the surface area of the cylinder. The volume formula for a cylinder, I guess we'd say that's SA as surface area. The volume of a cylinder is pi r squared, that's the area of the base, times the height of the cylinder. So we're going to be using these formulas coming up momentarily. So it says use the volume formula for a cylinder and the 500 cubic centimeter volume above and solve for h. So we have the volume of the cylinder is pi r squared h. That's the volume formula. We were told the volume needs to be 500 cubic centimeters for the can. And we were never told what the radius or the height is. Notice in the original question, never told the radius or the height. So we just have r squared h, and the directions encourage us to solve for h. So to solve for h, we're going to isolate this h right here and move everything to the other side. So we're going to divide both sides by pi r squared. So that would give us h equals 500 divided by pi r squared. So that's it for that. We're not solving for r. We want an expression for the volume, but to be in terms of h rather than v, since we know what v is, 500. Next it says substitute your answer to be into the surface area formula. So the surface area formula was this, 2 pi r squared plus 2 pi r h. We're going to substitute this expression, 500 pi r squared, in where the h is, and the h is right there. It says simplify as much as possible. So we would have the surface area is 2 pi r squared plus 2 pi r times h, and h is 500 divided by pi r squared. And can we simplify that at all? We actually can. So we can divide pi and pi and r with r squared. If that's hard for you to visualize, you could multiply across. So you'd get 2 pi r squared plus 2 times 500 is 1,000 pi r over pi r squared. And then maybe it's a little easier to see that you can divide pi and divide one of these r's out of the denominator. But you still have an r to the first in the denominator. So we would get this expression, the surface area in terms of one variable, r, is 2 pi r squared plus 1,000 divided by r. That's much simpler looking than we originally had at that point right there. And then we were told to graph the function using a table of values from r equals 1 to r equals 10, and then label our axes. So we're going to use this formula. The surface area is 2 pi r squared plus 1,000 divided by r. Making a table of values so we can graph. We're going to have r is what we're plugging in, and we're plugging in 1 all the way to 10 so we can get a good idea of what the shape looks like. We'll continue that over here, 8, 9, 10. And then the surface area, using that formula right above it. When I plug 1 in, you could take your calculators out and verify these numbers. But when I plug 1 in, I get 1,006 with a little bit of decimals. Plugging 2 in, I get 525, and then I get 390, and then I get 351, and then 357, 392, 451. I'll pause there, and you might be asking, where in the world are you getting these numbers? So for instance, for the 525 number, I would do 2 pi 2 squared plus 1,000 over 2 to get this value of 525. So I'm plugging in the various radii into where the radii are in the formula. And then for 8, I get 527, surface area, 527. And then I get 620, and then 728. So we're going to graph these values. We have the radius is the value we're plugging into the function. So that's our radius in centimeters. And then this axis is the surface area, and that would be square centimeters. So what we've done is we have a constraint of a volume having to be a certain amount. So we solved in an earlier part with that volume to kind of merge the two equations, volume and surface area, into one equation so that we could graph it based on one variable, the radius. So plotting these points, we have 1, 1,000, basically. 1, 1,000 is right about here. We have 2, 500 and some, which might be right about here. 3, 390, which is right about here. 4, 350, 5, 350-ish again. 6, about 400-ish. 7 is 450. 8 is 520, 7 some. 9 is 620. And then 10 is 700 and some. So it looks like our function looks something like this. So again, don't forget what the context is. The question that we're trying to answer is, what radius do we want that will minimize the surface area? The surface area is what we have plotted on the y-axis. The radius is what we have plotted on the x-axis. So what radius would give a minimum? So looking at this graph, can you tell where the minimum is? The minimum amount of metal used to create the cylinder. What is the minimum amount of metal needed? So on the first part, you're going to be answering as a try this, what radius, approximately, what radius would we want to use? And then with that given radius, with the radius whatever you chose, then what would the actual surface area be of the shape? Using the formula that we had originally, what surface area would correspond to that radius? So, good luck on this try this. Feel free to email your teachers if you have any questions about it. Thanks for watching this video, and I will see you next time.